To begin to understand organic compounds a little bit better, we'll have to take a look at some of their common features. Organic compounds, since they're based on the element carbon, are going to have covalent bonding. So we have nonmetals that are involved in organic compounds. We can review and think about what we learned in a previous chapter about Lewis structures and the Octet Rule, and it helps us kind of understand how these organic molecules are put together. So remember, all organic compounds will contain carbon, and carbon's best friend is hydrogen. And so it's very common for organic compounds to contain both carbon and hydrogen. The Octet Rule, which tells us that all elements like to be surrounded by 8 electrons, except for the hydrogen, which can only have 2, lets us predict how many bonds these two elements would like to form. In a slide that's to come, I'll have this written down as well. So carbon likes to form 4 bonds and have 0 lone pairs. Now those bonds can be single, double, or triple bonds when it's formed to other carbon atoms. Remember that we would draw a single bond as one line and represents 2 electrons. A double bond has 2 lines, and a triple bond would have 3 lines. In part, it's because carbon has ability to form single, double, and triple bonds with each other that we have millions of compounds that can involve carbon. You can see here these carbons may have chains, which would be a string of carbons. So I'll just have here a chain of 3 carbons. So a chain would simply be where you had one carbon after another. And this particular thing I'm drawing only contains carbon and hydrogen. And something that we might not have seen before, carbons can also form rings. But I'm not the best at drawing rings. This would be a 6-member ring. But carbon can form rings with itself and include other elements. And that's something we haven't really looked at before. Now remind yourself that hydrogen will only form 1 bond, and everything I've drawn so far has shown that, and it will have 0 lone pairs. It's because hydrogen can only have 2 electrons. Remember, each bond that's drawn, each single bond represents 2 electrons. Now we can have other elements other than hydrogen and carbon, and any element that's not hydrogen or carbon is called a hetero atom. So elements that are not carbon and hydrogen are called hetero atoms. There are several common ones that you can see here, including nitrogen, oxygen, and the halogens, which would be fluorine, chlorine, bromine, and iodine. You may also see things like sulfur. So again, just to emphasize, because it's often a point of confusion, if in your text or homework they mention the word heteroatom, it's just talking about any atom that is not carbon and hydrogen. So we're going to be drawing structures of organic molecules. And if you recall, when we learned to draw Lewis structures, we had to count up valence electrons and place them around central atoms so that each element would have 8, except the hydrogen, which would only have 2. Now, in organic chemistry, the atoms tend to follow the Octet Rule very well. So instead of counting up all the elements, the valence electrons for the elements and placing them, we can use the predictions we have based on the octet rule. Another reason this is so very valuable and helpful is that organic molecules can tend to be large, and so this is a helpful way for figuring out the structure that they would have. So how many bonds do we predict from each one of the elements in organic molecules? Well, if you recall, if we look at the group number, that will tell us the number of valence electrons. And we know that each element, except for hydrogen, likes to have 8 electrons around it. So we can predict the number of bonds based on how many valence electrons they have and what it would take to make 8. So group 5A, like nitrogen, would like 3 bonds. Group 6A would like 2, because 6 plus 2 is 8. 7A would like 1, because 7 plus 1 is 8. Carbon, which I mentioned earlier, has 4 valence electrons, so it would like 4 bonds, 4 plus 4. And hydrogen can only have 1 bond because it can have only 2 electrons around it. Now each bond represents 2 electrons. So just thinking about it, if I had 3 bonds, that would only represent 6 electrons. So that can't be the whole story. So what makes the octet, or the 8 electrons, is the lone pairs. So with 3 bonds, you would also need 1 lone pair. So we predict nitrogen has 3 bonds and 1 lone pair. Oxygen, if it has 2 bonds, that would be 4 electrons, it would need 2 lone pairs. So when we see oxygen, we predict that it will have 2 bonds and 2 lone pairs. The halogens in group 7A, we predict 1 bond, which would only represent 2 electrons. So to have 8 total, we would need 3 lone pairs. Carbon with 4 bonds would represent 8 electrons, so it, we predict, has no lone pairs, and hydrogen will never have a lone pair. So let me erase this so we can look at this chart. This chart's going to help us predict how many bonds and how each element would have and how many lone pairs, as well as to help us then complete a Lewis structure. So let's look at these examples below. And there's a homework problem like this. It says fill in hydrogens, which is how we fill in with a hydrogen. We're going to use hydrogen to add bonds and lone pairs in each compound. So here I have on letter A, I have all carbons. So each carbon needs 4 bonds. So this carbon has 1. So I would need to add 3 hydrogens, which would represent then 4 bonds. The second carbon here has 1, 2, 3 bonds already. So it would just need 1 more to make a total of 4. It would not matter if I wrote it above or below. I tend to write it in this example above simply so I don't run into the example below it. The next carbon right here has 1, 2, 3. So that would have 4 by adding a hydrogen. And this the last carbon here has 1. So I need 2, 3, 4. Now in this example, I did not need any lone pairs because we see carbon has 4 bonds and 0 lone pairs. So let's look at letter B. And I just usually go from left to right, but it really doesn't matter. So this carbon right here has 1 bond. So I would add 3 hydrogens to make it have 4. The next carbon has 1, 2, 3. So I would add one more to add 4. And this last carbon has 1. I'll add 2, 3, 4. Now I did not do the oxygen. And oxygen, looking up here, needs 2 bonds and 2 lone pairs, so it has 1 bond. So I'd add 1 more bond and then 2 lone pairs. So I'm using this chart up here to help me figure out how many bonds and lone pairs. So let's do letter C. So this carbon has 1 bond, and so carbon needs 4, so that's 2, 3, 4. This carbon has 1, 2, 3, 4, so I wouldn't add anything. Now nitrogen, I look up here, nitrogen needs 3 bonds and 1 lone pair, so it has 1, 2, I'll add a 3rd bond, 3, because that's what the directions say, and then a lone pair. And I could have written the hydrogen above and the lone pair on the bottom. Either way is fine. And then this carbon here has 1, so I need 2, 3, 4. And then I didn't do the oxygen, so there's oxygen, and it has 1, 2 bonds, which is good already because oxygen needs 2 and 2, so I'd need my 2 lone pairs. Let me erase this again up here so we can see it better on the last example. Okay, so then letter D. This isn't a ring, but you do it the same way. Here's a carbon, and it has 1, 2 bonds, and carbon needs 4 bonds and no lone pairs. So that's 1, 2, 3, 4. And then this carbon has 1, 2, so it's 3, 4. And then oxygen, I see, needs 2 bonds and 2 lone pairs, and it has 1, 2, and so it would need 2 lone pairs. Let me redraw that one. I made it kind of messy because I had to draw the lines so much. Okay, so it would have 2 here, 2 here, and 2 lone pairs. So again, in these directions, it just said to fill in the hydrogens, which means that when you fill in a hydrogen, it means you're just adding a single bond and then also lone pairs. It did not tell me I could make a double bond or anything else, so I'm just following the directions.